So the ideas of conservation laws are just, as we discussed in the lectures, the fundamental principle at the end of the day is something like nothing comes out of nothing, right? Ex nihilo nihil fit. So we wouldn't expect that if we put in a box certain objects and then we close and seal the box, and the box is properly isolated from the rest of the things outside of the box. In other words, there is no interference from, no interaction coming from the from the outside. Excuse me. We would expect that if we wait whichever amount of time we want, once we open that, we expect to find the same objects. So this is an idea that you also have sort of ingrained because you have studied before some science, and for instance the law of conservation of mass and Lavoisier and so forth. But might be a little more difficult to observe that the same thing applies not only to the amount of material or the amount of stuff that there is in the box, that we could also make something similar about the amount of motion that there is in the box. So take for instance the box and put one of the objects, kick one of the objects and put it in motion. If you close the box, indeed, yeah, when you open, you expect to have, if you wait for long enough, you say everything is going to be stable, right? Nothing is going to be moving. But the truth is that that's just because we have friction. So once we account for friction, we can expect then that if we close we put some object in motion, we close the box and we wait some time, we expect to find actually the same amount of motion, not necessarily with the same object. Objects might have been broken into pieces and reconfigured in different ways, but the total amount of motion, whatever that is, needs to be the same, right? So what we see in a case of linear momentum is precisely a definition of something that can translate as the amount of linear motion. Remember, motion is of two types. There's linear motion or translational motion, and there's rotational motion. In particular, we have been studying motion in a line as the as the most simpler case, and also motion in a circle as the most simple case for rotational motion. And we're going to be using those ideas again to introduce those two concepts of two different amounts of motion. One amount of motion is going to be related to the translational motion, which is what we call linear momentum, and one is going to be, as we will see in the next video, on angular momentum, right? Now the first thing that we can see is precisely linear momentum, defined as P, and that's just the product of the mass times the velocity of an object. So if you want to find what's the linear momentum or the amount of momentum you wish to think in that way of an object, we define the amount of momentum as just the product of the mass times the velocity, right? And this makes sense if we compare to scenarios. For instance, there's a train going at 5 miles per hour and a kid riding his bike at 5 miles per hour. We somehow intuitively come with the idea that there's more motion in the train. Why is that? Because of the mass. Again, that's inertia. That's the opposition to the change of the state of motion. But we also see that the same object, for instance, the same kid going 5 miles per hour or 100 miles per hour, somehow he could go 100 miles per hour, is going to be completely different. And that's where we see velocity coming here. This idea is already in the theory of impetus from Buridan, but mathematically we start to see them now with the cars. And that's why we say this is a linear momentum. And that's sort of the idea of how much motion there is in a translational type of motion. Now the thing that we can see is that this derived from the formula of force equals mass acceleration, and then we just said that, okay, in Newton we know that if something is happening, in other words, if some velocity is not the same at the beginning and at the end, that is, there is a change in velocity. That is, we can define an acceleration, which is the rate of change of that velocity in time, which of course is not going to be non-zero. It's not going to be zero, and that means there is a force. So we identify the force as the cause that produces an acceleration that is a change in the velocity, that is a change in the state of motion. And from this equation we saw that, of course, we can just rewrite the force as mass times the change in velocity over time, which means that we can write the force times delta t as the mass times the change in velocity, right? So of course we define this as the impulse. That's force times delta t, which is the impulse. It's not the same if I'm applying the same force for 1 second or 3 seconds. The longer that I'm applying the force, the more impulse. In other words, the more amount of motion I'm going to have. And this part over here that we can rewrite just simply as mv minus v sub 0. That's mv minus mv sub 0, and then we identified this as p. We just made that definition ourselves, and this is the initial momentum. And if that's the case, then we can see that this is the difference between initial and final momentum, and that can be defined as the increment or the change in momentum. So then we can rewrite everything in here. We saw that the law says that J is equal to the change in momentum. And this is the principle of conservation of momentum. Now, we typically can say it the other way. Let's write it for the type of arguments we're going to make, maybe more comfortable, we just invert it, but of course it's inequality, so it doesn't really matter. Now, one very important thing here is that J, remember, this is force times delta T, but what sort of forces are we considering? We're only considering external forces to the system, right? Why only external forces to the system? Because every force that acts in a system, if I have a system, I define a box, and I have two objects, an object is going to come and collide with the other one, the force that this object does on this is going to be the same, but opposite to the force that this object does on that. And so they're going to produce inverse forces. So the one force is going to be acting here, and then the amount of motion is going to be the same. It only matters when I come from the outside and I interfere with the system with a force from the outside, so an external force, and that's what's going to be accounted by impulse. And of course, if impulse is zero, meaning if the system is really isolated, then there needs to be no change in the state of motion, right? If I say that the impulse is zero, then that means that the change in P is equal to zero. That means the P it's equal to P sub 0. Basically, there is no change in the state of motion. And this is the law we're saying, unless there are external interactions, unless there is any external interference that are, of course, the result of forces coming from the outside, my system is going to remain with the same amount of motion. Linear momentum is going to be conserved. And this is very useful to solve several problems, when instead of actually making maybe analysis of forces or that, we're going to make an analysis of what's the amount of motion at the beginning and what's the amount of motion at the end. Just on a last important thing, it's very important, it's critical that you identify clearly at the beginning of your problem what elements constitute your system. Your system is, so to speak, like a small universe. I'm defining the system, I'm defining the universe where I'm studying everything. Of course, there's not going to be like the universe as in our universe, but just like a local universe. And that universe has things outside. Those are the things that are going to be responsible for interacting with our system and producing the impulse, right? But otherwise, everything that's at the beginning needs to be at the end, also in the amount of motion. Let's see some problems. So we have mentioned momentum is a vector, right? Because momentum is actually the product of the mass times the velocity of an object. And so that means that momentum is going to have direction and magnitude, which means that the direction and magnitude need to be conserved. We could make the analysis for magnitude to make sure that it's conserved, but we also should be able to observe that thing. So how do we describe that? Actually, well, because it's a vector, we're all going to be working in two dimensions. So we do what we've been doing for the entire course. Describe the momentum in the horizontal component, and describe the momentum in the vertical component. Whatever that components are, right? We saw in the case of the inclined plane, for instance, that the vertical was this one and then the horizontal this one was much more convenient than actually defining the traditional horizontal and vertical, right? So the direction that you define horizontal and vertical is going to depend on the geometry or the symmetry of the problem. But the first thing you're going to do is just describe it as horizontal and vertical motion. And once you have that, then you're going to apply the conservation of momentum for the horizontal, which is the result of the, and for the vertical, which is for the result of the impulse on the horizontal and the vertical components, right? And then you can just describe them as independent from each other, because again, motion is independent on every direction. We said that for the velocities, and this is the product of velocity. So if I can describe my velocity as indistinct to horizontal and vertical, then I'm certainly going to be able to do that with horizontal and vertical components of the momentum. What about the J? J is just simply the force times delta T. And this is a vector because force is a vector, but I can decompose the force into the horizontal and vertical. So I will be able to decompose into the horizontal and vertical of the impulse. I can put in here and then solve the problem. So the first thing we're going to always see, as we've been doing always before, as soon as we have two-dimensional, we're going to decompose horizontal and vertical, and then we're going to use them independently. And so we're going to then see initial for horizontal component versus final of horizontal component, right? Or final of horizontal component. And the same, initial of vertical, final vertical. And we're going to do this accounting approach to physics, always distributing between vertical and horizontal. At the end, we can recompose to make sure that the total amount of momentum we're conserving, and so forth. But this is just the basic idea that we're going to see in every single problem of this chapter. So the application of the conservation laws is pretty much akin to the situation where you, let's say, make some cookies and leave it there in the kitchen, and there's a child around, right? And you know the child is looking at the cookies, he wants to eat some, and let's say there are 5 cookies, right? And so you say, well, how many cookies do there need to be at the end? Well, there need to be 5, but what if there are 4? Well, you know that the child took the cookie. If there was no child in the kitchen, and the cookies went from 5 to 4, then you would expect something came into the room to distort that. But if nothing came, then it's impossible to go from 5 to 4, right? That's the principle of conservation. But once we account for the fact that things internally can change, basically I had 5 cookies and a hungry child, I have 4 cookies and a child fed, then somehow I have transferred that from the amount of cookies to the child, right? And so we're going to see this same thing in terms of motion with the objects that take part in our scenario. So in problem number 2 of discussions, we have that there are 2 girls with masses M1 and M2. This is roller skates, but let's just make a standard skate because it's easier to, right, to draw, right? And the idea here is that both have mass 1 and mass 2. And they're close to each other and face to face, right? And now girl number 1 is going to be pushing. She has long arms. And then she pushes girl number 2 and sends number 2 moving backwards. So assuming the girls move freely on their skates, with what speed does girl move 1? So we want to know what happens to 1. So in conservation momentum, first we need to identify the systems, and we can do something akin to the free body diagram in forces. Now I'm going to represent girl number 1 and girl number 2 if you wish, right? We can even make just circles. And let's say this is the initial time. So what about number 1? What's the velocity of the mass of 1 is m1 and the velocity of 1 is 0. They're at rest. What about object 2? It's a mass 2 and the velocity of 2 is 0. So let's put sub 0 here to identify velocity initial, right? 0. And then we can identify what happens at the end. What do we observe at the end? Well, at the end I observe that masses are the same. We're not changing the mass, but I observe that this object is moving backwards. So because I draw them this way, I'm assuming backwards as being this the positive. Of course, if you consider this 1 and this 2, it would go the other way. It's not the same. So we have a B2 which is different from 0 now, and the question is what's going on with number 1? What happens to V1? That's the thing that we're trying to solve. So now, of course, if we define our system as containing only girl number 1 and girl number 2 and nothing else, then there's nothing interacting in this system, right? You could consider, well, there's gravity and all those things. But these ideas of conservation laws are very practical because we're moving away from actually forces. So, of course, we're going to need to identify if there are any forces external to the system. But in this case, there are no external forces in the system because we're not analyzing the motion in the vertical direction. So as we said, because momentum is a vector, you always have to distribute into horizontal and vertical components. And for each one of those components, momentum is going to be conserved unless there's a force acting on that direction. And because we are only analyzing the horizontal component of the motion in this case, even if there's weight, which presumably will be vertical, that is not going to affect the horizontal component of the motion, so I can apply that with no force. So again, the question is there any external force? In other words, is there any force being applied not by the girl number 1 or girl number 2 acting on the girls at some point that's going to produce an impulse that's going to change the momentum in the x direction? Well, that's not anymore a vector, it's just a component. So is there anyone? No. So what's the force? Excuse me, the force is 0, so that means the impulse is going to be 0. So that means that if I calculate the total momentum at the beginning, which is of course going to be girl number 1 plus girl number 2, we can just keep this 0, 0, and we could identify this as the x, but because this is one dimension, we don't need to do it. But understand, if this was a vector, you would have to decompose. If it was a two-dimensional situation, and then we can calculate the total momentum at the end, which is going to be P1 plus P2. Well, let's identify the numbers. P1 sub 0. What's P1 sub 0? It's going to be mass 1 times V sub 1. How much is V sub 1? 0. So how much is this? 0. The total amount of momentum at the beginning is 0. What about P2? Well, P2 is 0. So mass 2 is V2, excuse me. So mass 2 is mass 2, excuse me. That's the situation we're seeing. And this is the initial one, right? So what's the velocity initial? Also 0. So what's the momentum? 0. So then what's the total momentum at the beginning? 0. Now let's go for the final. So momentum of P1 is going to be, at the end, is going to be m1, And then velocity 1. Do we know velocity 1? No, that's actually what we're trying to solve for. So let's keep it that way. And what about P2? Well, for P2 we know that it's M2 times V2, which we don't know, but somehow we know it's non-zero, so that remains this way, which means that the total momentum at the end is of course going to be M1 V1 plus M2 V2. And now again, we go back and say, this difference, how much it needs to be? 0. So we can solve for that, so let's erase here. So what's the change in momentum? Which is P minus P sub 0, so total of course. So how much is that? That's going to be M1 V1 plus M2 V2 minus, that's this, minus the initial momentum, which is 0, that's going to be 0. Why? Because there's no external force. Now look at this situation. If there was someone coming and my system, I have defined the system as girl 1 plus girl 2, that's my entire system. If a third girl comes and pushes girl number 1, for instance, that will be an external force in my description of the system, because girl number 3 will not be part of the system. But because girl number 1 is indeed pushing number 2, but girl number 1 is part of the system, that's not considered as an external force. That's by definition internal to the system, right? And of course, that means that the impulse, external impulse is 0. So once I write for this, I can just write mv1 is going to be m2 v2, and finally that v1 is going to be minus m2 divided by m1 v1, excuse me, v2. So this is the solution, this is the force, this is the velocity of girl number 1. Very important thing here, I have defined this axis, let's say, as the positive, and I've said girl number 2 is moving that direction. What's going to happen to girl number 1? It's going to go the other way. This is similar to, this is actually recoil. When we studied recoil before, in the case of action-reaction forces, with momentum we're going to see it very easily. Because we're going to see that the girl pushes that girl this way, that girl is going to be pushing that girl the other way, action-reaction. In terms of momentum, if this girl was stationary and is moving, the momentum needs to come from somewhere. Because she didn't have any motion to give, then what she needs to do is compensate for that motion moving in the other way, so with negative motion. And of course, how fast they're going to go if both girls were the same weight, if M2 is equal to M1, if they both were as massive. That doesn't sound nice talking about girls, but if they were both girls as massive, then they would move with the same velocity but in opposite directions. If one is heavier than the other, the one will move more than the other. For instance, take the scenario where instead of being another girl, there is a wall. The mass of the wall you can consider is sort of infinite. So how much would be how much would be the velocity of one? In this case, the momentum. She would need to impart the momentum to the other one. So you would see that girl 1 would be moving. How much is the wall going to be moving? Well, if the wall is infinite, that's going to go to 0. So basically, it doesn't matter if there's a certain velocity. This kind of cancel. So what's actually happens in real world, nothing is infinite. Right? So it's going to be very big mass. So you can play with the ratio of the masses and then see that the ratio of velocity is going to be related to the ratio of the masses, right? We can see that directly here. So V1 to V2 is going to be proportional to M2 over M1, right? So, this is correct. So then that's what we're, forget about the sign if you wish. Basically the sign is telling you opposite directions. But the ratio of velocity is going to be the inverse with the ratio of the masses, but inverted, right? So the higher the mass, this is then, right, the lower the velocity, because again the amount of motion needs to be conserved. So basically from this equation we could just replace numbers, but this is just to see indeed this is what happens. If you stay on the skater and you push your friend moves to that way, you move to the other way. Why? Because you both have 0 motion at the beginning, but you're having some motion at the end. How do you compensate for that? Because actually the amount of motion of one is the same but opposite to the amount of motion of the other, and so they cancel each other. We have 0 motion, and then indeed we are conserving motion. So from here we can see how by accounting for the amount of motion at the beginning and at the end we can figure out something that we were missing, because we are forced by the conditions of the problem that the motion needs to be conserved because there are no external forces acting on the problem. Let's see another one. So in problem number 3 of discussions, we're going to have a 2 kilogram brick that is moving at a velocity of 6 meters per second, and we're being asked how much force do we need to apply such that the brick stops, basically that the brick comes to a final velocity of 0 meters per second in an amount of time of 7, 10 to the minus 4 seconds, so 0.7 milliseconds, right? Okay, so how do we produce that force? So again, this comes from the principle of conservation of momentum. If momentum is the difference, the change in momentum is due to J, and we're gonna go from moving to no moving, I'm gonna be changing velocity, so I'm gonna be changing momentum. I need something that responds or explains why the motion is just disappearing. Things do not pop into existence, they do not vanish out of existence. That will break all principles of rationality on which science is built. So how do we explain that? Because there's an interaction from something external to the system. So we're being asked how much of that interaction is necessary, right? And so J is F delta T. We got delta T, so let's write it. And we have this, which is going to be delta P is going to be P minus P sub 0. Well, how much is P? P is going to be M times V, P sub 0, M times V sub 0. And J, it's equal to what? The force, which we're trying to find, delta T, which we have in there. So from this, we can say delta P is equal to J. In other words, that the mass V minus mass V sub 0 needs to be equal to F times delta T. We're trying to solve for F, so of course that's going to be mass V. Let's write it down here. That's going to be mass V minus mass V sub 0 divided by delta T. That's equal to the force. If we replace numbers, what's the mass? That's 2 kilograms times the velocity, or 6, final velocity is 0, minus mass at the beginning is 2, at the end is the velocity 6, and delta T, it's 7 10 to the minus 4, right? So of course that's minus 12, so that's minus 12 divided by 10 to the minus 4. So if we use the calculator, we can see that the force is going to be minus 1.7, and that's going to be 10 to the 4 newtons. So, important thing, force is negative, which means if the object was coming to a stop, the impulse needs to be opposite to the motion, because the input is in the impulse is in the direction of the force, and we know that when you are decelerating, you have a negative acceleration, which necessarily means that the force is pointing in the opposite way. So again, everything is obviously consistent, but basically that's the solution. Now the idea of impulse is a very interesting one, because this is something we understand intuitively. So let's say that you were driving a truck, right? And then let's say that you're designing, for instance, a racetrack, and then drivers sometimes get out of the track and they're gonna hit something, and then you wanna make them come to a stop. So how do you make them come to a stop? Obviously the velocity needs to stop, this needs to end. But here's the thing, so let's say if you write, this is the car, if you just say, oh, I'm gonna build a wall, what we're gonna observe is that the impulse, the change in velocity is going to be the same, right? So the change in momentum, so the change in velocity here is going to be the same as the change in velocity if instead of doing this, I do, for instance, a stack of hay, let's say, right? Haystack. So this object is moving here, and at the beginning both are moving with the same mass and the same velocity, and at the end both are with velocity equal to 0. So here my goal, both cases, is coming from motion with the same velocity to no motion at all. And here is the difference of this idea of impulse. So in both cases, because the change in momentum is going to be the same, the impulse required is the same. But there's two ways of achieving that impulse. One, as in this case, has a very large force in a very little amount of time. And in this case, we're going to have a much higher time of interaction, and so we need a lesser force. So of course, if your goal is not to kill everyone, you don't build a wall, you build some structure where the force can be lower to produce that change in state of motion. And how do you compensate for that? You compensate for that with time, and the other way, right? If your goal was just to destroy the car, then you will build a wall and you will not build a strong structure, right? So this is the idea of when we're applying a force, and the force acts the same amount of force in different time produces a different impulse, but the same impulse can be applied either with a lower force in a higher time of interaction, or a higher force in a lower time of interaction. So in problem number 4, we're going to have a slightly different scenario, which is also interesting to see. Not always you're going to have two objects and at the end you have the same amount of objects. Sometimes you have less amount of objects because the objects they merge, so to speak, or they become one, or they just split into many more objects. The amount of objects is not the magnitude, there's not a quantity that needs to be conserved. The amount of stuff maybe, which we will see later, but the amount of things, no, what matters is the amount of motion and the amount of fundamental thing that is in there, right? And we're gonna see an example in here in elastic collisions, as they're sometimes called, which corresponds to the case of objects. There are two objects at the beginning and there's one object at the end. How do I analyze that? Well, in this case, there is railroad going at 10,000 kilograms, railroad car traveling at the speed of 24 meters per second, and strikes an identical railroad car. So the mass of object 2 is going to be the same, 10,000 kilograms, because it's identical. And the initial velocity is 0 because it's at rest, right? So this object is moving and this is at rest. And it says if the cars lock together as a result of the collision, so this is the initial situation, what's going to happen at the end? It happens that both become one, like a marriage. So they collide and they become one, and what is the common velocity afterwards? So we could even call this velocity 3, and we say what's going on in here? What's the velocity, right? So how do we analyze this scenario? Well, conservation of momentum. So the system is what? Railroad 1, railroad car 1, and railroad car 2. So my system, right, I identify that my system is railroad car 1 and railroad car 2, which is just a combination of both. It doesn't mean that I need to have the same, I need to have the same amount of momentum, which is from the point of view I'm analyzing, but doesn't mean I need to have the same amount of objects. And what I'm going to see is that at the beginning, I'm going to see railroad motion of 1 is going to be mass of 1 times velocity of 1. I have those numbers. So let's say 1 at the beginning. And momentum of object 2 at the beginning is what? Mass 2 times v sub 2 0. Now this is 0, so of course this is going to be 0, and this is non-zero. We can replace the number, it's going to be 24, so it's 240,000 kilograms per meter per second, right? 24 times 10,000, 0 times 10,000, that's 0. So what's the total initial momentum? Was P1 sub 0 plus P2 sub 0, and that's equal to what? That's equal to 240,000 kilograms per meter per second. So that is the first part, that's the initial. So what happens at the end? Well, we had car 1 and car 2, so even if they break apart, at the end, this system needs to compress whatever it compressed before. So if this contains car 1 and car 2, does this contain 1 and 2? Yes. So now it's going to be a new object made of 1 and 2, but this is still all that was in my system. So at the end, I'm only going to have what I can call momentum 3, which is going to be the mass 3 times velocity 3. But how much is the mass of 3? Well, it's the mass of 1 plus the mass of 2. That's what, again, the math, this is the physics to make, physics uses the math to express these ideas, but we need to know the concepts, and we need to identify the things we're discussing, otherwise it's impossible to do this, right? So, mass 1 was 10,000 and mass 2, so I can identify that mass 3 is indeed the sum of 1 and 2, right? There's no information in the problem that says that maybe, hey, they lose the rear bump or something like that. They have the same mass. So, both masses is 20,000, and that's going to be 20,000 kilograms times the velocity of 3, which I don't know what's that velocity, I need to find. So how do I solve the problem? Conservation of momentum. And the first thing I need to do at this point is to realize, is there any external impulse? In other words, are there any external forces interacting in my system made of 1 and 2? No, they're none. So how much is this? This is 0. So how much is the change in momentum? 0. So momentum needs to be conserved. So the initial momentum and the final momentum need to be the same, right? And this is, by the way, the total momentum at the end, because I only have object 3. So now I need to subtract total at the end minus total at the beginning, and that needs to be 0, which means that the total at the end needs to be equal to the total at the beginning. The total at the end is 20,000 V3. The total at the beginning was 240,000 kilograms per meter. Let's save the units, and then we can solve for V3. And so we are going to find 240,000 divided by 20,000, right? And that's going to be 12 meters per second, which makes sense, yes. So 4 zeros goes, and then 24 divided by 2. So 12 meters per second. So what's going on at the beginning? There's a car moving with 24 meters per second, and this is stationary. This comes, hit them, and they go slower. Fast, slower. Why slower? Because the amount of motion needs to be the same. And so I had a lot of motion going from here, and I'm going to have the same amount of motion at the end, but now I need to distribute it with a bigger mass, because now I have both masses together. So I'm conserving the motion. There's no force. If then someone was pushing from the outside, then the situation would be different, because we will be gaining momentum. So we will not necessarily have them the same at the beginning and at the end, but that difference will be given by the amount of force, by the amount, of impulse, which is the amount of motion that we're introducing from the outside. This is the idea always of conservation of momentum. Sometimes momentum or objects will be moving with a velocity that is not in a single direction. We have seen that. We need to decompose. This is an example of that. Problem number 8 on discussion says there's 7,500 the cars, the railroad cars, and the trucks are all the same. The mass is 7,500 kilograms, and it's traveling at 5 meters per second east. So, well, you're inverted, so I don't know. But that's going to be moving in this direction, let's say, and that's 5 meters per second. So, right? So, and it collides with the 1,500 kilograms. Let's say this is east. Let's write it for the time being. And now it's going to collide with a car moving at 20 meters per second in a direction 30 degrees south of west, right? So if you write north, south, east, and west, which might be inverted because of the way this is recorded, then what you're going to see is that it's 30 degrees south of west. So you get west, and you go towards the south, how much? 30 degrees. So this is the velocity. So that's going to be the velocity of object number 2. Right? So basically I'm going to have a car moving like that. With what's the mass of car number 2? 1,500. Oh, this is actually a car. Okay, so this is a truck, and this is a proper car. And then 20 meters per second. And it's moving at 20 meters per second with a direction that we will identify from here. And the question is, with the two objects remain tangled together at the end. So this is a bad crash. So they crash against each other, and they become one. So imagine if the cars were coming here, what would you expect to happen, right? Something that you can wonder. Then you're going to see mathematically anyway, right? This is coming here. In terms of velocity, maybe like something like this, but this has velocity here, so they're certainly going to go down. The only matter is if they're going down vertically or down towards the left, depending on the proportions of the amount of motion that this has and this has. If this has more amount of momentum, it will go this way. If this has more amount of motion, this way. And if both have the same amount of momentum in the horizontal component, of course, it will be moving downwards. But we'll see it specifically. So they become one. So let's just make the crash here. This was one, and this is the other. So that's supposed to be, and this is going somewhere. We don't know where. We don't know the velocity. But because there's nothing lost, we certainly know what? That the mass at the end, so this is the end, this is the beginning, and this is the end. This is certainly the end, yes. So this mass here, mass 3, is of course mass 2. And this is going to be mass 1, and this is going to be mass 2, and this is going to be V2 sub 0, and this is going to be V1 sub 0. And this is V3, we don't know. Right? And that's actually the question, with what speed and what direction this is going. So how do we solve this? Again, conservation of momentum. But the very first thing we do, Remember, we have two dimensions, so let's express everything in terms of vectors. So for object number 1, we have the initial velocity, and that's given by what? Is 5 meters east. So if we define east as positive, that's 5 meters in x and 0 in y. What about object 2? Object 2, has what? We need to decompose. So what is going in the horizontal direction? Well, that is the adjacent of this one. So if it's the adjacent, so k, toa, so that's the cosine. So we're going to have 20 meters per second times the cosine of 30. What about the vertical? Well, that's the opposite of 30, so that's going to be the sine. So we're going to write 20 times sine of 30. And very important, this is, so to speak, the math. Let's see that this makes sense from our physics perspective. X is 20 cosine of 30, but it's opposite, so correct for the minus. Y is going downwards, correct the minus. And then now we have that thing, we can treat this object as conservation in x and conservation in y. So we can do that either by using vectors. If you're not comfortable using vectors, then just use distribute into horizontal and component and vertical component. So let's do conservation in horizontal. Before we do that, let's analyze. Is there any change? Is there any forces acting from the outside in the horizontal? No. So the change in horizontal is 0. Are there any changes in the vertical? No. External to the system. Of course, there's changes in the vertical because one is hitting the other, but there's no changes coming from the outside. Those are all internal. Sorry. Those are all internal, so that means this is 0, so this is 0. So the vertical and horizontal components of the force need to be conserved. So let's do first, maybe for instance, horizontal. So what do we do horizontal? Let's see if we can get one less annoying. Okay, horizontal. So horizontal, we're gonna have the beginning. Let's say here the initial. So we write the initial is what? We can finally, by the way, because delta px is 0, that means that px minus px sub 0 is 0, which means that px is equal to px sub 0, right? Basically, the amount of motion needs to be the same at the beginning and at the end. So what I'm going to write is that the initial needs to be the same as the final. So let's write here the initial and here the final, and then we solve. So horizontal, you can do this whichever way you like, right? Horizontal at the beginning, we have what? This object of mass 1. We're going to have mass 1 times the velocity, x component, v1x sub 0, plus what? Mass 2 times v2x sub 0, and that's equal to what? Well, to mass 3 times v sub 3x. That's not sub 0, now it's final, and this needs to be the same. So let's replace numbers. It's 7,500 times 5 plus 1,500 times what? Cosine of 30 times 20. That's 0.86 times 20. That's going to be 1.7, something like that. So 17, excuse me. Let's say 17, but negative. So let's write minus 17. Yeah, something like that. 17, and that's equal to the mass 3, which is mass 1 plus 2, which is 8,000, 9,000, times velocity 3, which we don't know. So we can make these numbers. That's 7,500 times 5, which is going to be 3,800 minus, so let's use the calculator quickly. So this is going to be 25,500. This is 37, by the way, and then this is going to be 9,000 V3. So if we solve for V3, we're going to find the V3 is 1.33 positive, which means it's traveling in this direction. So now we know it's going to go in this direction. How much over the horizontal is depending on how much the vertical, which is purely given by that anyways. So that's the horizontal x component. So that's the first solution. What about the vertical? So let's write the vertical analysis. And again, the vertical needs to be conserved. So that means that delta py is sub 0, which means that p sub y sub 0, it's the same as p sub y, right? The total momentum at the beginning and at the end. Let's write the initial. What's the initial? vertically, how much? Mass 1 v1 y0 plus mass 2 vy, mass 2 vy2 sub 0, it's equal to mass 3, it's equal to the final. How much is the final? Mass 3 v3 sub y. And what do we know here? What's the y velocity initial? 0. So that's going to be mass 1 times 0. So that's going to be 0 plus mass 2 is 1500. What about the velocity in y2? It's 20 times sine of 30. Sine of 30 is 1/2. So that's minus 10. And that's equal to a mass 3. How much is mass 3? We said it's 9,000 times v3 sub y. So if we actually solve for v3 sub y, we're going to find that that's minus 15,000 divided by 9,000, which this cancels, and then we have 1.66, no? Approx 1.77 negative. So that's going to be minus 1.77. So how much was the velocity initially going down? It's only this component of this car, and that's actually minus 10 meters per second. So the vertical component was minus 10 meters per second. But at the end, the vertical component is only 1.7 or 1.8. So why did we lose vertical motion? Because what matters is not just the velocity, what matters is the amount of motion. And the amount of motion at the beginning was 10 times 15,000. And now if we multiply 1.7 times, sorry, that's 1.7, just 1.7. If we multiply 1.7 times 9,000, which 1.6 is 9,000, that should give us 15,000, right? Because it's 2/3 of that, so it's 6,000 plus 9,000. So that's 1.7 negative. So now we see we're conserving that amount vertical and horizontal. Of course, this is after imposing that, right? But we're saying how the object was moving very fast like this way, but then they're moving like more slowly, and they're still moving in horizontal, right? So this were like, this was slow but massive, this was faster, and then they just move like that. So kind of like this. Let's figure out, excuse me, let's figure out what is the direction of this velocity. So now we're going to have what? The velocity for number 3, it's given as v3 sub x, v3 sub y, of course. And that's equal to what? To 1.33 positive in this direction and negative 1.7 in the y direction meters per second. So let's draw again, excuse me, north, south, east, west, and we're going to see, we're going to put 1.33 in the horizontal and 1.7 in the vertical. So actually, excuse me, minus 1.7 vertically. So about that. So what's going to be moving like this. And now the question is, of course, what is the angle of that, right? Which we could say south of east, if we can express that angle. So how do we determine that angle? Well, we have what? We have two sides. We have the adjacent, and we have, which is, excuse me, let's write it. We have the adjacent, which is v sub 3x, and we have the opposite, which is v sub 3y. So what can I do? Well, the tangent of theta, this being theta, is the opposite divided by contiguous, adjacent. And that means what? Minus 1.7, or let's just keep it 1.7. You can do that if you wish. And then 1.33. If you make that, you find that theta is 52 degrees, 52.5, something like that, degrees. Okay? But then what? If I express 52.5 degrees and I was telling someone who didn't know, they would expect typically that it's above the horizontal. So it's actually, we could say it's minus 52.5 degrees, or we could do 360 plus minus 52 degrees to actually find that what you're going to be doing is 307.5 degrees in this direction, right? Or you can express this 52.5 degrees south of east. So we had, according to the problem, a car moving at 20 meters per second, making 30 degrees south of west. The wreckage is going to be moving 52.5 degrees south of east. And if you're a forensic team and you go to the scene of a wreckage, you can figure out velocities at the beginning and the end by knowing all these things. Of course, there are certain assumptions that we're not discussing here, that this is not going to be perfectly elastic or perfectly inelastic or things like that. There are going to be losses because cars are stopping and all that. But at least you have an idea of how the accident worked out. Why? Because things do not just start moving or stop moving out of nothing. There needs to be a reason. There needs to be an impulse that accounts for the change of motion. So again, another example of linear momentum used for accounting, for accountability, for counting, the amount of motion and making sure that at the beginning and the end, the amount of motion is the same. Now, problem 9 is another example of that type of scenario where we have motions happening in two directions. So it says that we have a ball of 800 grams. So directly we can write the mass is 0.8 kilograms, moving at 30 centimeters per second, which of course is 0.3 meters per second, right? And it's moving in the horizontal direction. And then it's gonna come to collide with another ball of mass 500 grams, which is 0.5 kilograms, which is moving with a velocity of 50 centimeters per second, which we can immediately transfer into meters per second to save any issues, any hassle. So let's write 0.3 meters per second, and let's write that this is v sub 0, 1, v sub 1, 0, excuse me, this is v sub 2, 0. So what we're being told is that after the collision, mass of 800 grams, which is M1, this is the initial. After M, what we know on the final is that the 800 grams ball, which is M1, has a speed of final of 1, not initial, final, of 15 centimeters per second, which is 0.15 meters per second. Now we expect, according to the diagram, which you can find in the solution, that the object, this is given, otherwise it would be impossible to know. The object actually what's happening is that they go like this, that one mass is going down, the other one is going up after the end, right? After the collision, they collide and they just go at an angle. And what's that angle? Well, in the case of let's write it here, let's make it more explicit, maybe here. So at the beginning we had mass 1 that goes here and goes this way, that's mass 1, and we're going to have mass 2 that goes this way, collides, and goes that way, right? So they interact here. This is actually pretty similar diagrams to the ones that you see in particle physics, in scattering problems. Two objects come in, but they scatter, and they go in different directions. It's not anymore like purely horizontal. We're given this angle. That angle is 30 degrees. Again, it's in the solutions. And the diagram, I mean, the rest of the solution you have to figure out, and then we don't know that for object number 2. So this is number 2 and this is number 1, right? So they will come like this and go like that. Okay, so we need to figure out what? We need to figure out what is the velocity v2 after the collision, right? v2 being the 500. So again, let's write initial and let's write final. Question: is there any force? Are there any forces interacting with these objects? Well, no. And by the way, this you might say, what about weight in here? In momentum, we're almost always ignoring gravitation force. So imagine that you're doing these experiments in space. First of all, because weight is going to be acting anyways and because we're not considering vertical motion. Basically, vertical understood as I drop an object, but vertical understood like in a table, I can describe up and down and left and right, but I'm not saying up and down like this. So gravitation doesn't change for any of them, right? So that you can discount it altogether and just ignore gravity unless it's explicitly asked, right? So then that's the thing. So for instance, if I was having a problem where there's a cannonball hitting and the ball's doing something like that, then in that case I would have to include gravity. How do I include gravity? Through the impulse, right? And the impulse will be acting during the entire time of the motion, because the force of gravity is constant and it's acting always in the motion, right? But we are not seeing that sort of complex problems. These problems are always assuming very trivial stuff, and in this case we can assume there is no forces acting. Very good. So what do we have? We need to find the velocity. So let's do initial and final accounting. Why? Because the change in momentum is going to be external, which in our case means that the change in x needs to be the impulse in x, and the change in y needs to be the impulse in y. Always remember that you distinguish. And what's the impulse in x? 0. What's the impulse in y? 0. There's no interactions coming from the outside, which means that the change in momentums are going to be 0, which means that initial and final momentums need to be the same, both in vertical and horizontal. So that's about that. Yeah, very good. So let's do that. Let's do horizontal first, and let's write initial here. So what's the initial horizontal? Well, let's because these objects are going like this, we can actually write all the vectors. Let's write the vectors velocities in here. So what do we know? Velocity of 1 at the beginning is a vector that has x component of 0.3 and a y component of 0. It's not moving, it's just moving horizontally. Velocity of 1 at the end. Well, that's going to be what? This is going like this and then going like that, right? So let's do this. So it kind of becomes more obvious, as we just did there. So what is the horizontal component of V1? What is that? That's this one over here. Which is that? That's the adjacent of that angle. So what's that? So Katoa, that's cosine. So that's going to be 0.3 times, we don't know that velocity, or were we told? Yeah, that's 15. Now it's not 0.3, now it's 0.15. We were told that's the final velocity times the cosine of 30. What about the y? That's going to be opposite, right? That's then sine. So that's going to be 0.15, which is the final velocity of object 1 times the sine of 30. That's vector velocity 1. Let's do vector velocity 2 at the beginning. And by the way, this is positive, but this one is going down, so that's negative. What about V2 sub 0, initial of 0? So this is moving that way. This is moving this way. This is moving that way. And this is moving this way, 1 sub 0, right? Very good. So what about V2 sub 0? Well, that's 0.5 meters per second x and 0 y. And what about final? Well, that's actually what we're trying to find. So what if we write it like this? And then we'll solve for x and y, and then figure out what's the direction and everything to solve the final, to finish the problem. So let's come back here, and let's say, what's the horizontal situation? Well, I have m1 v1 sub 0. That's the amount of momentum of this object, plus the amount of momentum of this object. How much momentum in there? Well, that's m2 v2 sub 0. And that needs to be equal to the n amount of momentum. How much is the ball here? That's m1 times v sub 1, not v sub 1 sub 0, just v sub 1, plus m2 times v sub 2. And again, not this v sub 2, not that initial v sub 2. And now we can replace numbers. So m sub 1 is 0.8. How much is the initial x? Of course, all of these components are x, So you want to write them x, x, x. So it's only these ones. So how much is the v sub 1 sub 0 x? 0.3. So it's 0.8 times 0.3 plus m sub 2, 0.5 times v sub 2 sub 0. v sub 2 sub 0, 0.5. But I forgot, this is actually v sub 2 sub 0 is 0.5 in x, but negative. So actually this is minus 0.5. And what about v sub 2? We can leave it without the sign, and then the numbers will become negative. Or if you add the number, the negative, then you can introduce it here, and then the numbers, the results are going to be positive. So you can, I suggest you don't put the number yet, because it's not a number. Whenever it's not a number, just don't put sign. Just keep the numbers like that, and then figure out and make the sanity check that what we expect according to the diagram is that v sub 2x is horizontal, and it's going in that direction, so this number needs to be negative. And what we expect is that the y is positive, so we expect that number to be positive. So if we did properly the problem, this is going to be negative, this is going to be positive, right? But we keep them that way. Okay, then mass sub 1. How much is mass sub 1? 0.8 times what? Velocity 1 at the end. Velocity 1 at the end is 0.15 times cosine of 30. So cosine of 30 is 0.86, which means that we're going to have about 13. I think this is about 13. 0.13, I mean 0.13 plus m sub 2 v sub 2 x. So m sub 2 is still 0.5. What about v sub 2x? We don't know, so we keep v sub 2x. So let's make this calculation. That's going to be 0.24 minus 0.25 equal to I think it's 0.10, right? Then 4 plus 0.5 v sub 2x. This, so I can solve for v sub 2x. This is 0.01, right? Divided by 0.104, it's equal to 0. Oh, no, excuse me. Let's go step by step then. So how much is this minus this? This is minus 0.01, and I'm gonna subtract minus 0.104, and that's equal to 0.5 v sub 2 sub x, which means this and this is minus 0.10. So that's going to be minus 0.10 divided by, actually that will be 5 now, divided by 0.5, which of course is minus 0.21, and that's equal to v sub 2 x. So how much is that? X 0.21 negative, which we expected from the diagram. The horizontal needs to be negative. 0.25, 0.21 negative. Okay, let's erase this and do the same but for the vertical. So for vertical, we're going to do the same, initial and final. So let's write the initial. What are the initial? Well, the initial vertical components are m1 in the 1y plus m2 in the 2 initial y component, and that needs to be the same as mass 1 into the 1 sub y final plus m mass 2 into the v into mass 2 plus times, excuse me, too many things, too many subscript, velocity final in the y component of object 2. Okay, so let's replace. So mass 1 is still 0.8 times what's the velocity initial in the y component? 0. So that's 0. Plus mass 2, 0.5. What's the vertical initial of 0? Excuse me, of object 2? 0. Mass 1, 0.8 times vertical of 1 final. That's this one. This is 1/2. So that's going to be minus 0.075, right? So yeah, so times 0.0 times 0.75, and now negative plus, because it's negative, that's a negative, plus the mass 2, which is 0.5, times v sub 2y, which is keep it like that. What do we expect the sign of this to be? Well, this is v sub 2, which is velocity of 2, final, object 2 at the end, vertical component. The vertical component is going upwards. So we expect this to be positive. Let's see if we did it well. So how much is this? This is 0 equals to what? That's 0.8 times that number over there. So let's use this instrument of calculation. That's going to be, I think it's 0.06. So that's going to be minus 0.06. Oh, yeah. So that's going to be minus 0.06 plus 0.5 v sub 2y, which means that v sub 2y it's going to be equal to what? To 0.06 divided by 0.5, which is 0.12 meters per second. What did we obtain? 0.12 meters per second. Everything is meters per second, positive, as expected. So now we see that the velocity is going to have a negative component and vertical component. And then we can even find the angle. How do we find the angle? Let's make a diagram again. Let's take as much space as possible. So let's analyze object 2. How is object 2 moving? Well, it's moving with 0.21x negative, so let's say that's about that. And it's moving with 0.12, about half of that, vertically. So let's say something like this, right? So vertically, so something like this. So how much is that going to be? Well, you have to add them together, right? So that's going to be this. So that's going to be the final velocity of the vector, right? Something like that. Well, let's make it larger, right? So let's make it larger. So let's say this much, so we can just keep it like this. That's going to be v2. Where this is how much? Well, this is v sub 2y, and this is v sub 2x. So if we call this theta, what do we know? That with respect to theta, v sub 2x is the adjacent, v sub 2y is the opposite, right? That's the opposite, which is the y component. So opposite divided by adjacent is, of course, tangent. So what we know is the tangent of theta is the opposite, v sub 2y, divided by v sub 2x, which is 0.12 divided by 0.21. That's going to be about 0.5, which I think is going to be about 30 degrees, so 29 degrees, something like that. And again, I haven't used the signs, so now I need to correct. So 29 degrees is 29 degrees north of, if this is west, north of west, or north of, again, in my perspective, the image is mirror. So this is west, right, on the left. So 29 degrees. So if I actually want to go from x to y, as is typically the case, the elevation needs to be 180 minus 29. So that will be like 151. Or, yeah, 151, there's nothing else to say, right? So this angle here will be 151, which is the same as saying 90 minus 29 plus 90, right? Anyway, so that would be the other way of saying that. But in any case, we have found the direction. How much is the velocity? Then you do the square of this plus the square of this, and then the magnitude, right? So let's say velocity of 2 is going to be what? It's going to be 0.12 squared plus 0.21 squared, and that square of root, if we do that, 0.24 meters per second. So it's about 24 centimeters per second moving in that direction. So basically we find finally the velocity, and we have the entire description of the movement. Once we know the initial conditions, we can calculate how much is the total amount of motion there's in here. At the end, we know the amount of motion in another part of the system, and we ask, hey, what about that one? Well, you can figure out how much is that one based on the principle of conservation of momentum, which again applies in this particular case because it's isolated system, meaning there are no external forces acting on the system. If there were external forces in the system, for instance, if there was friction and the surface that produces the friction is not considered in the system, that will be an external force. But as we saw, if you consider the friction to be in the system, if you consider the ground to be in your system, then there will be no external forces. But you would have to see that whatever motion you lose is the one that the floor is actually gaining, which makes sense again from the point of view of action and reaction. You can see that on the skate. If you jump from, or if you just take a step forward in the skate, you go forward, the skate will go backwards. If you consider your system at the end, mass of the skate and velocity going negative, mass of your and velocity there going positive, both need to match, because if you were at rest at the beginning and you're moving at the end, both combine. Makes sense. Whereas if you don't take the skate into your system, the skate being the floor, then you're going to be gaining momentum. Who's making that momentum? The friction of the skate, which in this case is external, right? So again, that makes sense. We need to be careful with the systems, observe with things considered or not. And once we have defined the system, then we can see whether in our system there are any external forces acting or not. In this particular case, there were none, so we know impulse is 0, which means momentum is conserved. Based on momentum conservation, initial needs to be the same as the end, and always, 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 always. It doesn't matter if you're in 1 and 2 dimensions. You always, it does matter, but basically in 2 dimensions, you always split it into horizontal and vertical components and treat them independently, because conservation of momentum needs to be also acting independently, because motion is independent in the 2 directions.